Assalamualaikum warahmatullahi wabarakatuh and good day to everyone. So I will continue my lecture on this course, Advanced Thermodynamics, MME6154, for the fourth chapter, the first law of thermodynamics. In this chapter, we will learn about the energy transfer by heat and also moving boundary work. These two chapters are actually available in Thermodynamics by Chennel at chapter 2 and also chapter 4 respectively. So for moving boundary work, we will learn on the calculation for polytropic process, isobaric process, isothermal process, and isovolume process. Okay, in this subtopic, we will see the difference or what are the definition of these processes are. And also we will learn about the energy balance for closed system, okay, for constant pressure expansion or compression process, okay, and also we will touch on specific heats, Cp and Cv, and we will also learn about the internal energy, enthalpy, and specific heats of ideal gases, and also for incompressible substances such as solids and liquid. Okay, let's start our lecture for chapter 4. In first chapter, I believe everyone already understand what is the definition of first law of thermodynamics. Okay, we already know that in first law, it is stated that energy cannot be created nor destroyed. It can only change form. Okay, let's see one situation here. We can see a cold soda left on a table eventually warms up. Okay, so heat transferred into the soda, okay, 16 joule per second, okay, over time, okay, 8 joule per second, and almost become to no heat transfer. So when a body is left in a medium that is at a different temperature, energy transfer in the form of heat, okay, where higher temperature body to lower takes place between the body and the surrounding medium until thermal equilibrium is established. So for this situation, we have a room air 25 degree and the can of soda, okay, cold soda 5 degrees Celsius. Okay, after some times, some heat was transferred into the can of soda until the thermal equilibrium is established, where no heat transfer happen anymore, and the cold soda becomes the same temperature with the surrounding 25 degree. Energy can cross the boundary of a closed system in two distinct forms, energy and work. Okay, here we already understand in chapter 1 about this closed system, and in closed system, only energy can cross the system boundary. So now we already know that the energy can cross the boundary in two distinct forms. Okay, energy, okay, in this situation, heat, and also work. During an interaction between a system and its surrounding, the amount of energy gained by the system must be exactly equal to the amount of energy lost by the surroundings. So actually, from this sentence, okay, uh, we actually can derive the energy balance equation. Okay, so the change in internal energy of a system is equal to the heat added to the system minus the work done by the system. So we get delta U change in internal energy, okay, internal energy equal to Q heat added to the system minus W work done by the system. Okay. So heat or heat transfer. What is heat transfer? Okay. Heat transfer is the form of energy that is transferred between two systems or a system and its surrounding by a virtue of temperature difference. Okay, the heat transfer only can happen when there is a temperature difference, okay, between system or between system and surrounding. Heat is energy transition. It is recognized only as it crosses the boundary of a system. A process during which there is no heat transfer is called an adiabatic process. So remember, if in the question stated adiabatic process means no heat transfer happen in the system. Okay, what is adiabatic process? Adiabatic process is where the system is well insulated so that only negligible amount of heat can pass through the boundary. Okay, still, even though the system is well insulated, still some very small amount of heat or energy can pass through the boundary. However, it is a negligible level. So we call it as adiabatic process. Another condition is when both the system and the surrounding are at the same temperature. There's no driving force or temperature difference for heat transfer. So remember, already stated before that heat transfer only happen when there is a temperature difference. But when the system and the surrounding are at the same temperature, so we don't have the driving force or the temperature difference for heat transfer to happen. Okay, so I already explained for this example, okay, temperature difference is the driving force for heat transfer. The larger the temperature difference, the higher is the rate of heat transfer. Alright, so now energy transfer by heat. Heat transfer per unit mass. Okay, we always have this uh, uh, the property. Okay, so if heat property is Q, large Q. Okay, so per unit mass we usually use small q. Q equal to Q over M, kilojoule per kilogram. Okay, amount of heat transfer when heat transfer rate changes with time. So we have heat transfer rate Q dot. Okay, so when it is change with time, so we have T1 and T2. Okay, times with dt. So we will get the amount of heat transfer. Amount of heat transfer when heat transfer rate is constant. Okay, so Q equal to Q dot times with delta T. So I already gave two examples here. During an adiabatic process, a system exchanges no heat with its surrounding. So you can see by yourself, and actually in China also already written several few examples that you can refer to. Okay, so now we move on to the heat transfer mechanisms. Some of the equations that is familiar to us, which is conduction process, convection process, and also radiation process. So this is the equation for conduction rate. Okay, we have dot over there. Q dot conduction, Q dot convection, and Q dot radiation. So just a recap on what is the definition on conduction, convection, and radiation respectively. So for conduction, the transfer of energy from the more energetic particles of a substance to the adjacent less energetic ones as a result of interaction between particles. Okay, I believe you guys are already familiar with conduction process, and also convection. You guys are already familiar with this. The transfer of energy between a solid surface and the adjacent fluid that is in motion, and it involves the combined effects of conduction and fluid motion. And also we have the radiation process, the transfer of energy due to the emission of electromagnetic waves or photons. Okay, so these are the equations. Okay, you guys can see by yourself uh, or in the attached slides. Okay, so now let's see the heat transfer by work. Okay, heat transfer by work. Heat equal to work. Okay, last time we already explained to you that energy can cross the boundary of a closed system in two distinct forms, energy and work. So just now, okay, I already explained the boundary, the energy cross the boundary by heat, okay, by energy. So now I will explain on the energy cross the boundary by work. Okay, so now we are move on work. Okay, energy transfer by work. So heat equal to work. An energy interaction between a system and its surrounding. Energy can cross the boundary of a closed system in the form of heat or work. Okay, which I already explained just now. So work. Okay, what is work? Definition of work. Work is the energy transfer associated with a force acting through a distance or any energy interaction that is not caused by a temperature difference between the system and its surrounding. Okay, just now we explained about the energy transfer by heat. Okay, so energy transfer by heat only happen when there is a driving force, where the driving force means the temperature difference. However, in work, okay, where in energy transfer by work, it is not caused by temperature difference at all. Okay, so it is actually associated with a force acting through a distance. Okay, for example, a rising piston, a rotating shaft, and electric wire crossing the system boundaries are all associated with work interaction. Okay, units of work, you guys already know, energy units, kilojoule. Work done per unit mass of a system is denoted by small w equal to large W over m, kilojoule per kilogram. Work done per unit time is called power, okay, W dot, okay, with unit kilojoule per s second or kilowatt. Formal sign convention, okay, heat transfer to a system and work done by a system are positive. Heat transfer from a system and work done on a system are negative. Okay, you guys should take note on this because uh, might be come out in your exam. Alright, okay. So how far do you understand about the sign, okay, of this process? Either is positive or negative. Alright, so energy transfer by work, we have work 30 kilojoule, mass 2 kilogram, and delta T 5 seconds. So we have power W dot, okay, equal to 6 kilowatt, and we have the W small. What is small w? It is work per unit mass, okay, equal to 15 kilojoule per kilogram. So we have 30 kilojoule work, okay, happen in the system. And sometimes we also specifying direction of heat and work. So let's say in the system there are two both energy transfer happen between heat and also work. So we can actually put direction, okay, either it is in or out. Alright, so let's continue on 4.3, moving boundary work. So just now we already know the energy transfer to a system or out from a system uh, using by heat and work. Okay, so now we want to see about moving boundary work. So what is moving boundary work? Okay, one form of mechanical work frequently encountered in practice is associated with the expansion or compression of a gas in a piston cylinder device. During this process, part of the boundary, the inner face of the piston, moves back and forth. Therefore, the expansion and compression work is often called moving boundary work or simply boundary work. Okay, this process where the expansion and compression work happen. Okay, so it is called moving boundary work or simply boundary work. Moving boundary work equal to the primary form of work involved in automobile engines. During their expansion, the combustion gases force the piston to move, which in turn forces the crankshaft to rotate. So maybe you guys already familiar with this process inside our engine, okay, car engine, okay, where during the expansion, the combustion gas force the piston to move, and eventually the crankshaft will rotate. Okay, so the moving boundary work associated with real engines or compressors cannot be determined from thermodynamic analysis alone because the piston usually moves at very high speed, making it difficult for the gas inside the piston to maintain equilibrium. So guys, usually we calculate some processes, okay, when it is in equilibrium or when it is in clear state. Okay, we have initial state 1 and we have final state, okay, 2. So we have a clear state, state 1 and state 2. However, at the real situation, okay, it is difficult because usually the piston moves at very high speed. Okay, so it is difficult to make the piston to maintain in equilibrium. Thus, The states through which the system passes during the process cannot be specified and no process path can be drawn. So usually in the real situation, we cannot actually draw the PV diagram, okay, and we cannot actually specify each state, okay, clearly, okay. So no process path can be drawn, okay. So no process path can be drawn. So guys, how can we specify this kind of a situation? Okay, alright. So work being a path function cannot be determined analytically without a knowledge of a path. Therefore, the boundary work in real engines or compressors is determined by direct measurements. Okay, and here we call it as quasi-equilibrium process. Quasi means um, it is almost equilibrium process, but it is not equilibrium. Okay, since it is too fast, then we take that kind of that particular situation as quasi-equilibrium process. Okay, now quasi-equilibrium process. What is quasi-equilibrium process? A process during which the system remains nearly in equilibrium at all times, closely approximated the real engines, especially when the piston moves at low velocities. If the piston is allowed to move at a distant ds in quasi-equilibrium manner, the differential work done during the process is, okay, WB is moving boundary work, okay, boundary B and work W equal to force times width some distance, okay, ds, F times width ds. So F we are associated with pressure times with area times with ds. So from this PA times ds, it is equal P times with dV. So just now, it is the equation for uh, moving boundary work. Okay, so it is in the differential form. Okay, where the product of the absolute pressure and the differential change in the volume dV in the system. Okay, so we call this equation as moving boundary work. So usually in question, they will ask, okay, calculate moving boundary work for this particular system. Then this is the equation that you need to use. Okay, if we have several system altogether, then you have to add, okay, total boundary work by using integration. So one system from point 1 to point 2, how much the total moving boundary work, okay? The unit is kilojoule. So guys, pressure is always positive. The symbol that change in the work is depends on the volume. If the process is expansion, then the volume will be positive. If it is compression process, then it is negative. Okay. So in chapter 3, I believe, we already learned on pure substance, okay, where we learn how to write a diagram like this, pressure with volume diagram, okay, and we have process path 1 to process path 2. So we want to know the total moving boundary work of this process, okay, from process 1, state 1 to state 2. So how to get the total moving boundary work? By integration, okay, like I already explained just now, by integration of P times with dV. So this is actually equal to area below this process path. So if you write diagram like this, P and V, process path 1, process path 2. So below this area, okay, below this area is all total moving boundary work. Okay, you can actually write here WB, okay, boundary work. Okay, the area under the process curve on a PV diagram is equal in magnitude to the work done during a quasi-equilibrium expansion or compression process of a closed system. Okay, remember the area below the process path of in a diagram of PdV, it is actually equal to the total moving boundary work of the system. Alright. The boundary work done during a process depends on the path followed as well as the end states. So it depends on the area below the process path. So if A maybe the area is quite larger compared to B. That is why it's 10 kilojoule. Okay, WB 8 kilojoule, WC 5 kilojoule. Okay, because the area is smaller than A. The net work done during a cycle is the difference between the work done by the system and the work done on the system. Okay, alright. So I actually put some exercise for you to do by yourself. Okay, for example, this exercise 2. Below figure shows a frictionless piston cylinder device contains 5 kg of water vapor at 400 kilopascal and 300 degree. Heat is now transferred to the water vapor at a constant pressure until the temperature reaches 450 degree. Assume the piston is not attached to a shaft and the weight of the piston remains constant. Okay, there's no weight. Okay, so it is constant. So first you have to illustrate the process on a PV diagram. You already learned this on chapter 2. Okay, please illustrate PV diagram. Okay, and then determine the work done by the steam during this process. Please do it by yourself and you can refer the answer it here. Okay, I already calculate for you guys. Okay, and then we have another question. A stationary mass of gas is compressed without friction from an initial state of 0.3 meter cubic and 0.105 megapascal to a final state of 0.15 meter cubic and 0.105 megapascal. The pressure remain constant during the process. There is a transfer of heat, negative 37.6 kJ from the gas during the process. How much does the internal energy of the gas change? So please do this by yourself and refer to this answer that I already put it here for you guys. Alright, now we continue on chapter 4 by explaining about process. There are several types of process. First, we have polytropic process. Okay, and I believe you guys already know in chapter 3, okay, we already discuss about the ideal gas equation. Okay, PV equal to MRT. So during actual expansion and compression processes of gas, pressure and volume are often related by below equation. So during the actual expansion and compression process, the pressure and volume is related by this equation. Okay, this equation PVN equal to C. Okay, C is actually the polytropic process constant, and N is polytropic exponent constant. Okay, and this is usually will be given in the question. Okay, if they ask you if the question stated that this system is undergoing polytropic process, then you have to use this equation for moving boundary work. Okay, WB equal to P2V2 minus P1V1 over 1 over N. So this is the equation for polytropic process. Okay, equation for moving boundary work for polytropic process. So if the question stated that this system undergoing polytropic process, then this is the equation that you need to use to calculate the boundary work. Okay, WB. Since C equal to P1V1N equal to P2V2N for an ideal gas, above equation can be written as WB equal to MR T2 minus T1 over 1 minus N. So yeah, depends on the on the question. Okay, if it's ideal gas, then you have to use the ideal gas equation for moving boundary work of polytropic process. Okay, understand? Now, this is just another equation. If the n here is equal to 1, okay, then you can simplify the equation some more with WB equal to PV ln V2 minus V1. Okay, yeah, this is for polytropic process. Then we have isothermal process. Okay, isothermal we already learned before. It is a process during which the temperature remains constant. So isothermal means temperature constant. Okay, and we will get the equation for isothermal is WB equal to PV ln V2 minus over V1. And if it is for ideal gas, then you can use this equation, MRT ln V2 over V1. Okay, this is the equation for moving boundary work for isothermal process. Okay, so again, if the question stated that this is isothermal process, then you have to use this equation. You cannot use this equation. Okay, PDV. Okay, you have to use this equation. Okay, and now let's move on to isobaric process. So what is isobaric? Isobaric process means that pressure remain constant. Okay, if pressure remain constant, the equation for moving boundary work WB is equal to P0, okay, the constant pressure, times with V2 minus V1. Okay, so we have here V2, the final state of volume, okay, specific volume, minus with V1, okay, the initial state, V1. Okay, and now isochoric or isometric process. So if isochoric or isometric process, it is a process during which the specific volume remain constant. Since the volume remain constant, the heat transfer into or out the system does not the PV work, but only changes the internal energy. So piston is restricted to move so that the volume remain constant. Schematic and PV diagram for a isochoric process is written here. So if it is a isochoric process, then this is the equation that you need to use, and this is how you draw your PV diagram. Okay, since the volume is constant, that's why there's no changes in volume here. Okay, so initial state 1, initial state end state 2, okay, and pressure for initial state 1 500, end state 400. However, the volume or specific volume remain constant. So here I summarize the equation that is used for to calculate the moving boundary work for each type of process. We have a general equation, WB equal to PDV, isobaric, polytropic, isothermal, and another one we have isochoric, okay, isometric. Alright, here also I give you one exercise. You can do it by yourself. A piston cylinder initially contains 0.4 meter cubic of air at 100 kilopascal and 80 degree. The air is now compressed to 0.13 meter cubic in such a way that the temperature inside the cylinder remain constant. Okay, temperature inside the cylinder remain constant. So what process is this? Temperature constant means it is isothermal process. So you have to use this equation to calculate the work done during this process. So you can do it by yourself, and please refer to this answer that I already provided here. Okay. Remember guys, in order to answer this kind of questions, you are required to draw this PV diagram. Okay, once if you draw this PV diagram, you will be given extra mark. I mean, not extra mark, but you will be given full mark. If you didn't draw this diagram, then maybe we will minus 2 or 3 from your mark. Here also we have another exercise. Below figure shows a frictionless piston cylinder device contains 5 kg of water vapor at 400 kilopascal and 300 degree. Heat is now transferred to the water vapor at a constant pressure until the temperature reaches 450 degree. Assume the piston is not attached to a shaft and the weight of the piston remain constant. So now it is constant pressure. So what process is it? It is isobaric. So isobaric. First, you need to illustrate the process on a PV diagram and determine the work done by the steam during this process. So calculate the work using this equation for isobaric process. So this kind of question is quite easy, but I just want you to get used to calculate this kind of work, okay, done by a system. Okay, maybe in examination it is not this simple. Okay, you are required maybe to explain why it happened like that. Okay, so you need to really understand on how to calculate, how to use each of the equation, because you are in master level. So master level, you cannot just calculate and show the answer. you have to explain why it happened like that. Okay, here also I already include the answer. You can refer it by yourself. And also another question for you guys to do. I won't read it. You can read by yourself, and you can see my answer sheet at the that I already provided in the slide. Okay, all right. So now we already finished the first topic, okay, of chapter 1, where we learn about energy transfer by heat and also energy transfer by work, and we have to calculate the moving boundary work, okay, for polytropic process, isobaric process, isothermal, and isochoric process. Alright, next let's continue on energy balance for closed system, okay, where we will learn about the energy balance for a constant pressure expansion or compression process. Okay, so now the energy balance for closed system. Last time we already learned about a closed system. Okay, so in this topic we will discuss the energy balance equation for specifically closed system. We already know in closed system the energy can cross the system boundary. However, mass cannot cross or enter the system boundary. Alright, so total energy of a system on a unit mass, okay, E, small e equal to E, large E over M, kilojoule per kilogram. So you always see this kind of property per unit mass, and usually we call it as specific something. For example, specific density. Okay, so this one is total energy of a system on a unit mass. There's no specific name for this. Okay, so small e equal to large E over M. Okay, in total energy of a system can be calculated in macroscopic. Okay, so for macroscopic, it is a system that processes as a whole with respect to some outside reference frame, such as kinetic and potential energies. So we have this kind of energy in macroscopic. Okay, kinetic energy Ke equal to mv squared over 2. Okay, so on a unit mass, okay, kinetic energy, we write it as a small kinetic energy Ke, and then for potential energy Pe equal to mgz or mgh. So on a unit mass, smaller alphabet is used. Alright, so this is for microscopic energy. How about microscopic? Okay, microscopic, it is related to the molecular structure of a system and the degree of the molecular activity, independent of outside reference frame. The sum of all microscopic forms of energy is called the internal energy of a system, denoted with U. So why I explain this one? Okay, macroscopic and microscopic. This is because in energy balance equation, it is associated with these energies. Okay, so we have kinetic energy plus potential energy plus internal energy. Okay, that is why I explain this right now. Okay, so only two forms of energy interaction associated with closed system. First, heat transfer, if its driving force is temperature difference, and another one is work, okay, other than temperature difference. Okay, so let's see the equation. Energy balance for any system undergoing any process for closed system. Okay, E in minus E out equal to delta E system. Net energy transfer by heat, work, and mass. Okay, we learned that energy transfer for closed system only happen where between heat and also work. Okay, so the driving force for heat is temperature different, and for work is other than temperature different. And then equal to delta E system, change in internal kinetic potential energies. So we already know, just now I explained, in the energy balance equation, it is associated with kinetic energy, potential energy, and also internal energy. So let's see the energy balance equation here. Okay, I already put it here. E in minus E out equal to heat. Okay, Q in minus Q out. This is heat plus sorry, plus W in minus W out, this is work, okay, plus E mass in minus E mass out. Okay, this equation is actually can be written like this. Delta E system, okay, E in minus E out, equal to delta U internal energy, this is internal energy, plus delta KE, this is kinetic energy, plus delta potential energy, delta PE. Okay, then we substitute all the equation that we learned just now for internal energy, M times with U2 minus U1. This is specific internal energy, okay, but mass plus kinetic energy equation plus potential energy equation. So that is why I explained about this macroscopic and microscopic, because in energy balance equation it is associated with these three energies, okay, internal energies, kinetic energy, and also potential energy. Alright, most systems encountered in practice are stationary, where the changes in kinetic and potential energies are equal to zero. Okay, so when the system is stationary, so we don't have any changes in kinetic and potential energies. So you can just put this as zero, okay, except for delta U, internal energy. Q equal to 0 for adiabatic system, where because no heat transfer happen, so you can just include here as 0. W equal to 0 for system that involve no work interaction. E mass equal to 0 for closed system, because no mass transfer happen in closed system. So it depends on the question actually, guys. If the question stated that it is adiabatic system, okay, adiabatic system means that Q here will become 0. You just have to add work and also energy by mass. If it is stated that no work interaction happen in the system, then this term will be 0. W in minus W out will be 0. So you just have to add between the changes between heat and energy mass. And if it is stated that it is closed system, then automatically this term will be 0. Okay, E mass in minus E mass out equal to 0. Okay, so the same equation but in the rate form. Okay, E dot in minus E dot out. So the equation will be dE system over dt. Okay, differentiation. The total quantities are related to the quantities per unit time. Q equal to Q dot delta T. Okay, it's because it makes sense. Okay, because Q dot equal to Q over delta T. Okay, so Q equal to Q dot delta T. Same with work and also energy, delta energy. Energy balance per unit mass. Per unit mass, okay, we have delta in E in minus E out, small letter. So it is actually E large E over M. Okay, energy balance per unit mass. So I just simplify it here. So it is actually E large E over M in minus large E over M out. Okay, equal to delta large E system. Okay, so that is energy balance per unit mass. And then energy balance for a cycle. Okay, W net out equal to Q net in, or W dot net out equal to Q dot net in, because it is a cycle. Energy balance in differential form. Okay, it is the same actually, only it is in differential form. So I hope you understand on the energy balance equation, where it is associated with macroscopic terms, which are kinetic energy and potential energy, and also microscopic term, which is internal energy. Okay, I put some exercise here. You can do it by yourself. A rigid tank contains a hot fluid that is cooled while being stirred by a paddle wheel. Initially, the internal energy of the fluid is at 100 kJ. During the cooling process, the fluid loses 500 kJ of heat, and the paddle wheel does 100 kJ of work on the fluid. Determine the final internal energy of the fluid. Okay, so based on the equation, okay, energy balance equation, you have to calculate the internal energy. So I already put it here. So you can try to do it by yourself and refer to this answer. Alright, so another question for you. Okay, you can read it by yourself and try to do it by yourself and refer to this answer that I already provided in the slide. Okay, alright, so we move on to the specific heat. Okay, so in chapter 1, okay, we already learned about the definition of specific heat. I hope you still remember. Okay, specific heat means the energy required to raise the temperature of a unit mass of a substance by 1 degree in a specified way. In general, this energy depends on how the process is executed. It takes different amounts of energy to raise the temperature of identical masses of different substances by 1 degree. So for example, you have iron and you have water. So it is two different substances. However, the mass is the same, okay, 1 kilogram. Mass also the same, 1 kilogram. And the temperature from 20 degree to 30 degree. How to increase this energy, this temperature, okay, from 20 to 30 degree. So we have to add some amounts of energy. So for iron, okay, maybe we add some heat, okay, 4.5 kilojoule. Okay, however, for water, you need to add 41.8 kilojoule of energy in order to increase 20 degree to 30 degree Celsius. That is why the specific heat depends on substances. Not all substances have the same specific heat. Okay, that's a very easy example, easy to understand. So Cp is always greater than Cv. Cp is specific heat pressure. Okay, Cv is specific heat volume. Okay, constant volume. So in specific heat at constant volume Cv, the energy required to raise the temperature for the unit mass of a substance by 1 degree as the volume is maintained constant. And in specific heat at constant pressure, the pressure is maintained constant. You can see at this example, okay, volume is constant, pressure is constant, okay, and we added some energy, 3.12 kilojoule, okay, and we add some energy to this system, 5.919 kilojoule, okay, where the pressure is constant, okay. Alright. The formal definition of Cv and Cp, the equation in the figure are valid for any substance undergoing any process. Cv and Cp are properties, okay. It is a properties. Okay, Cv is related to the changes in internal energy, U, and Cp to the changes in enthalpy, H. A common unit for specific heat, okay, you have to remember this, kJ, kilogram degree Celsius, or kJ, kilogram Kelvin. Okay, by the way, most of the calculation, you need to make sure the unit, the end result unit, okay. Sometimes in the equation they use Kelvin, okay, or they use kilopascal in order to get the end result that is standard, okay. So you need to familiar with those units, okay. Either it is kilopascal or pascal, okay, either it use Kelvin or degree Celsius, okay. So in the equation that you use, you have to familiar with those units. Okay. Alright. The specific heat of a substance changes with temperature. Okay. This one you already understand just now. Okay. So actually we finish on energy balance for closed system. Delta E equal to delta U internal energy plus delta Q plus delta W. Okay? And for adiabatic process, no heat transfer means Q is 0. If it is no work, then W is 0. If it is a closed system, then the E mass is 0. Okay, specific heat also we touch a little bit on the definition and several equation for constant pressure and constant volume specific heat. And let's continue on the next topic, internal energy, enthalpy, and specific heat of ideal gases, okay, and also of incompressible substances, which is solids and liquids. Okay, now we will continue on the internal energy, enthalpy, specific heats of ideal gases. Okay, in chapter 3, we already learned about the ideal gas equation. Okay, ideal gas equation is actually the simplest and best known equation of state of for substance in the gas phase. Okay, and this equation predicts the PVT behavior of a gas quite accurately within some properly selected region. Okay, its name is ideal gas equation of state, or ideal gas relation, or ideal gas. Alright, so this is the equation where we can see the relation between internal energy and also the ideal gas. So here we have enthalpy, H equal to U, internal energy, plus moving boundary work. Okay, and how it relates with the ideal gas. And from these two equations, we will get this relation, H equal to U plus RT. Okay, the enthalpy of an ideal gas is also a function of temperature only. Okay, since U and H depend only on temperature, the specific heat, CV and CP also depend on temperature only. Okay, as stated in this equation. Therefore, at a given T, U, H, CV and CP of an ideal gas have fixed values regardless of the specific volume or pressure. Okay, so the internal energy and enthalpy change of an ideal gas can be calculated using this equation. Okay, delta U, delta H, and this is the changes between internal energy and enthalpy. Alright. At low pressures, all real gases approach ideal gas behavior, and therefore their specific heat depends on temperature only. And this specific heat of real gases at low pressures are called ideal gas specific heat or zero pressure specific heat, and often denoted with CP0 and CV0. Okay, and as you already know in chapter 2, this U and H data for a number of gases is actually have been tabulated, and we can actually read it from a table. Okay, and you can try to look at the table in Thermodynamics Chengel. And there are three ways of calculating delta U and delta H. Okay, the net change of internal energy and also change of enthalpy. Okay, so delta U equal to U2 minus U1. Okay, also we can use this equation, and also this equation CV average delta T. Okay, so first by using the tabulated U and H data. Okay, this is how we already used to use previously in chapter 1, 2 and 3. We can refer to table and just take the value. This is the easiest and most accurate way when tables are readily available. And the second way is by using the CV or CP relation, okay, as the function of temperature and performing the integration. Okay, this is very inconvenient for hand calculation but quite desirable for computerized calculation. The results obtained are very accurate. Okay, and then number 3, by using average specific heat, okay, this equation. This is very simple and certainly very convenient when property tables are not available. The result obtained are reasonably accurate if the temperature interval is not very large. Okay, that is for internal energy and enthalpy. Okay, this is just some relation between the one that I already explained just now. Okay, and now we continue on the internal energy, enthalpy, specific heat of ideal of solid and liquid. Okay, we have incompressible substance. Okay, what is incompressible substance? It is a substance whose specific volume is constant or density is constant. Okay, for example, we have this rock. Okay, solid and liquids are incompressible substance. Okay, for example, you can see from this figure, okay, the specific volume of incompressible substance remain constant during a process. Okay, solid, okay, constant, liquid also constant. The CV and CP values of incompressible substance are identical and are denoted by C. Okay, C equal to CV and CP. This is basically constant. So here we can see the equation for internal energy change. Okay, CV dt, because it is constant, then we can use a C times T dt. Okay, and also by using the second way. Okay, there are three methods that I already explained just now. For the second way, we can use the integration process, and the third way is by using the average of specific heat. Okay, so I believe that is all for the chapter 4, where we already touched on the several okay, several topics. Okay, first we learn about the energy transfer by heat and also energy transfer by work. Okay, and then from energy transfer by work, we learn about the moving boundary work. Okay, and after moving boundary work, WB, we learn about how to calculate the moving boundary work for polytropic process, for isobaric process, isothermal process, and also isovolume or isochoric process. And then we also learn the energy balance equation for closed system. Okay, and how it is happen for constant pressure expansion or compression process. And we also touch a little bit on the definition of constant specific heat for constant pressure and also constant volume. And we also learn on how to calculate the internal energy change, enthalpy change, and how it relates with specific heat of ideal gases, and also for those with incompressible substance. So I believe you can read more from Thermodynamics Chengel for have a further deeper understanding, and you can try to do calculation from the example tutorial question that I include in this video. Okay, thank you so much everyone. I will see you in chapter 5.